So the goal of this series of lectures is the following. So three things. First is to motivate and define this object known as a planar algebra. And second is to discuss in detail one example of a planar algebra. And third, if there is time, is to do one application of planar algebras to analysis. This is a theorem of Popa. I don't think I'll really be able to do much the way this preparation is going on. Okay, so let's begin with creating a planar algebra. So whatever I'm going to say now for the next 10 or 15 minutes, mathematically it's irrelevant to what I'm going to do later. But I think it's important to know where they arise, right? So planar algebra, so this is first, let me say, history. Actually, the subject itself is not very old. So in fact, even in prehistory, so let me begin with in 1983, Jones wrote this very influential paper, Index for Subfactors. So let me briefly explain what was done in this paper. So I need to make some definitions. So now what a one-Neumann algebra is. A factor is a one-Neumann algebra with trivial center. That is, the only elements in it that commute with everything is just the scalars, right? Scalar multiples of 1. Factors are classified into various types. Now we'll be interested in only one kind of factors. So a 2-1 factor is a factor. Sorry? A factor means it's a one-Neumann algebra whose center is trivial. Oh, center. That is Z of m. If m is the one-Neumann algebra, Z of m is the set of all x in m such that xy equals yx for all y. Z of m is just scalar multiples of the identity. No center, only scalars. So among the factors there are various kinds, and of the kinds we will only be interested in things called 2-1 factors, and 2-1 factors are those which is a factor which is infinite dimensional so we are not interested in finite dimensional one-Neumann algebras. It's an infinite dimensional one-Neumann algebra, and such that, and admitting a trace. So a trace is just a linear functional which satisfies tau of xy equals tau of yx. And say normalized, tau of 1 is 1. So it's an infinite dimensional one-Neumann algebra which has no center and which has a trace, and when it does have a trace, then the trace is unique. And has other properties. So the trace, this one-Neumann algebra comes with a God-given trace. Now 2-1, so this is a factor and 2-1 factor. Now, so this Jones paper is about subfactors. So a subfactor is, as you might imagine, a 2-1 subfactor is a pair n contained in M of factors. So it's basically an inclusion of one-dimensional algebras of a particular kind, infinite dimensional one-dimensional algebra admitting a trace. So that is, sorry? Unital inclusion, yeah, is a pair n in M of factors. So the inclusion is unital. Okay. So what Jones did in this paper was to define an invariant for this, for a pair, for the subfactor called its index. So this is a numerical invariant which he denoted by m colon n. So associated to a subfactor is a measure of its size called the index, and denoted so this is a positive, some positive real number which he associated to a subfactor.
What do you mean by inclusion is to be unital?
That means the 1, if you take the 1 in n, it should be the same as the 1 in M, right? It should not go, it should, yeah, it should be an inclusion map. It should not go to a projection. You can go to a projection in general, but it should be the 1 of M.
Maybe just say, for example, you can think of 2 by 2 matrices as a subset of 3 by 3 matrices by look at the top left corner. Look at the top left corner and then 0 at the bottom. So that is not a unital enclosure of M2 in M3. Because 1 of M2 did not match to 1 of M3.
Okay. So he defined this index, and one of the most surprising results that he showed in this paper is that the index is quantized. This is not going to be relevant for us, but this is an important result. So what does this mean? It can only take a certain set of values. So it takes values either greater than or equal to 4 or of the form (4 cos squared pi by n). So beyond 4 it can be anything, but less than 4 there is a countable set of values that this index takes. It can only be of this form. So that was one of the main results in this paper. Okay, so now when you look at this notation for the index, so it should remind you of Galois theory. So that looks very much like the degree of a field extension, and indeed the index shares many properties that field extension degrees satisfy. For instance, the index is multiplicative. That means if n and m in P are 2-1 factors, then P colon n is the product of P colon m and m colon n. That is some property that the index satisfies. And once you have something like this, it makes sense to ask, is this something really like Galois theory going on for one factor contained in another? Is there a Galois theory for subfactors? And this question was answered in some sense. Yes, there is a kind of Galois theory for subfactors. If you have a subfactor n in M, then there is something that you can associate to it which is like the Galois group. So this was initially called a paragroup by Piano. Now let me restrict. See, I said so he defined this index. The index can actually be an infinite or some positive value, some finite value. So let me restrict to the case where the index is finite. So Galois theory for finite index subfactors. I'm not going to say anything about this except to say that there is a kind of Galois theory for finite index subfactors. This depends on something called a paragroup. What is called a paragroup by Ocneanu, and around the same time something else, a substitute for this called a lambda lattice by Popa. Now if you look at the definitions of these things, they are pretty complicated, very complicated algebraic objects. They are a substitute for a group. The very name paragroup means standing for a group, right? So they are supposed to be a substitute for the Galois group, but nothing as simple as groups. They are pretty complicated objects and require a lot of manipulations to prove even simple things, right? They're quite hard to work with. Okay, then so that is the prehistory. Then in 1999, so Jones wrote another paper. This is called Planar Algebras 1. So in which he visualized the same invariant, what is called a paragroup or equivalently a lambda lattice, in terms of an object which he called planar algebras. And these planar algebras, they're still quite complicated objects. I mean, you can't get rid of all the complications, but nevertheless it's very nice and pictorial. Many proofs become extremely simple when viewed in terms of planar algebras. And so that this is the thing that we are going to look at. Let me just say, in the same, before I define a planar algebra, let me say something about, back to this paper, index for subfactors. So what did he do with this n in m? So one of the things that was done in that paper is something that he called the basic construction. So what this basic construction does is begins with n in m and produces n in m in P. So somehow he uses this n in m to produce a larger one where P is also a 2-1 factor, and the index of m in n is the same as that of m in P. So the basic construction is a process which takes one subfactor and produces a larger one, right? It starts with n in m and then produces m in P. And of course it has the same index, so there's no reason why you cannot repeat this construction and get one whole chain of subfactors. So iterating this gives a tower Now the numbering is a problem. So there are various kinds of numbering that are used in the literature. So I'll use the following numbering. So we'll call m0 as n, m as m1, p as m2, so on and so forth. So starting with a single subfactor, you have produced a whole tower of factors, each one contained in the other, and with the property that the index of any two nearby ones are all the same as the original index that you started with. Now not only you have a tower of subfactors, he also produced, in fact the whole thing was constructed, so in the MK. So starting with, we have n and m, and starting with the next one, M2, M3, M4, so on, there is a distinguished projection in this one-dimensional algebra. So in the Mk, there are certain distinguished projections Ek. Very remarkable property. So what are these remarkable properties? These remarkable properties can be expressed in terms of a couple of equations. So two of them. One is that Ei and Ej commute if I and j are far apart. So E1 will commute with E3, E4, E5, so on. E2 will commute with E4, E5, E6, so on. E3 commutes with E1, E5. Except neighboring ones, any two of the E's will commute. And what about neighboring ones? Ei plus minus 1 Ei is 1 over delta squared Ei. So this is a certain number where delta square is actually the index of the subfactor. So neighboring which one? Oh, no, I didn't. Sorry. Yeah. So this double arrow notation means commutes with. Ei and Ej commute if I and j are apart, and if I and j are successive nearby ones, then they satisfy the relation Ei plus minus 1 Ei is 1 over delta squared Ei, where delta squared is the index of this subfactor. So that's some positive number. I'll call that delta squared. Now using this in a subsequent paper, he constructed his famous Jones polynomial, for which he got the Fields Medal, among other things. Okay. So this is the rough history. So the planar algebra, this object arises from these kind of things. There are these projections and there are these tower of algebras, and these are exactly the ingredients that we will also see in planar algebras. Actually from this tower there's a even better tower, and so there is a derived tower. And so what is this derived tower? What you do is you take here in one-dimensional algebras, in factors, the first thing that we considered was the center. So we said the center must be trivial. The things in M that commute with everything in M is just scalars. But here you could consider the things in these higher ones which commute with everything in N. So for example, there's a derived tower, N commutant in N, N commutant in M, N commutant in M2, so on and so forth. So this is the things in N that commute with everything in N. This we know is just scalars because N is a factor. The things in M that commute with everything in N, the things in M2 that commute with everything in N, so on. So this is also a increasing number of algebras, and the remarkable thing is when the original one is a finite index, all of these are finite dimensional algebras. There is a derived tower of finite dimensional algebras. So one would think, of course, that this is a much more manageable thing. So you just have finite dimensional algebras to deal with. So one would hope to be able to understand this in some way. And planar algebras exactly encode all this information in some other form. Okay, that is much for the history. Now, nothing of what I said is going to be used. This is just only for motivation, so that you know why we are going to study planar algebras. It's because they arise in the context of subfactors. But the definitions, on the other hand, are completely self-contained and make no reference to any analysis. What I want to do for the rest of the talk is to define what a planar algebra is. Now before I can define what a planar algebra is, I have to define an object called a planar tangle. So that's what I'm going to do. A planar tangle is a subset of the plane together with various associated data. So what kind of subset? So let me draw it. Yeah. So to begin with, this is a, I'll refine it later. So to begin with, this is a certain subset of the plane. So what kind of subset? So the kind of subsets that we are interested in arise in the following way. You take one big disk in the plane. Let me draw it big. And inside this big disk, you take several smaller disks. Okay. So punch out. So punch all these disks out and look at what remains, right? So you have this whole thing minus these holes, these 5 holes, right? So that is the subset of the plane that I am interested in. So I'll keep writing here and keep drawing here. So the first ingredient is it has an external disk. Normally it's denoted D0 and several internal disks. D1, D2. Some number. That number could well be 0. I'll address that issue later, right? I can punch 0 or more holes in this big disk, right? So each one is, here in this case, I have punched 5 holes in this big disk. And several internal disks denoted D1 to DB and labeled so. So let me make it clear that you must label your disks. I must know which one is D1, which one is D2, so on. So let me call. So this outside disk is normally D0.
Is
So
it important to specify the plane and RN or
it's important to specify
the plane? Which plane you are taking this subset of? This
Some plane.
plane, just R2, in R2, in the plane. That's why planar algebra, right? It has to do with that plane. So everything is happening in this plane. No, not Rn, R2, only plane. It's tied down very closely to plane. It's not 3. It's only plane. So in this case there are 5 disks. I'll label them D1, D2. Let me call this D3, D4, D5. So that is the first ingredient, an external disk and several internal disks labeled, all of them labeled. There is, so I can call this one D2 and that one D1, right? That would be a different tangle though. The tangle data comes with this labeling. So if I call this one D2 and this one D1, I'll be defining another planar tangle, not the same one as this, right? So this data of labeling comes along with the tangle. Okay, then, so this is the first thing. Then on each boundary circle, there are an even number of mark points. So these disks have these boundary circles. On each boundary circle, mark of an even number of points. I have to look up to make sure I get the example right. So for example, on this one, let me mark 6 points. Okay. On this one, I'll mark 4 points. On this one also, I mark 4 points. And on the rest, on these two, I do not mark any points at all. And on the outside disk, I mark . So on each boundary circle, there is an even number of marked points. That even number could well be 0, as in the case of this or that one. Even on the outside, it's possible that for a certain tangle, you could have no marked points on the outside. In this case, you have 6 marked points on the outside, 6 for this one, 4 for this one, 4 for this one, and 0 for these two. Okay. Then there are strings. So I'll explain what these are. First, let me draw them, and then I'll explain what strings are. So I have drawn these strings in blue color. So what are these strings? Strings come in. Did I what? Oh, there are two. Oh, there are two. Yeah. Is there any pattern? Well, you can do it any way you want, subject to certain rules. I'll explain the rules. Okay, so let me explain what are strings and what are the rules that govern drawing these strings. So then there are strings of two kinds. Two kinds, open and closed. So as you can see, these strings which join two marked points, some two marked points on these disks, these are what I'll call open strings. They have two endpoints. And then these strings are what I'll call closed strings. They are just strings floating around. They have no endpoints. They are just closed strings. So there are two kinds of strings, open and closed. Open strings have marked points as endpoints, while closed strings are just simple closed curves. I still haven't said what the rules are. These strings, first of all, cannot intersect, right? These strings cannot, as you see, I've drawn it in such a way. I have not drawn a string like this and another string crossing like that. No intersections are allowed. Strings must not intersect. That's one rule governing strings. Another rule is every marked point must be the end point of some string. I am not allowed to have a marked point just languishing by itself. So marked point must be the end point of a string. Only one string, right? Because I am not even allowed to intersect there. I cannot draw another thing like this here. Then those two strings would intersect at that boundary point. So these are the rules that govern strings. Okay, so we have these marked points, we have strings. Okay, then we have another rule. Ah, yes. Yeah, oh, okay, yes. Right. Okay. So another thing is these strings are not allowed to tangentially touch the boundaries of the disk. So the strings must tangential at the point of intersection. It must be a transverse intersection. With the boundaries. Right? So these strings cut at these boundaries, so they are not allowed to cut in a tangential manner. It must be only a transverse intersection. Right? So there must be a definite angle that they form there. Okay. So then we have something called the shading. As you can see, before we can define planar algebras, I have to tell you what a planar tangle is. A planar tangle itself has so much of data associated with it. Further, we need the data of shading. So in order to say what the shading is, so let me first define regions. So a region is a connected component of the complement of the strings and the internal disks. That's just a formal definition. You can see what the regions are. So for example, this thing is one region. This thing here, with the exception of this disk, whatever is here is another region. Here's a region. Here's a region. So you can see that there are several regions here. And what the shading requirement says is, so the tangle complement in the big disk. Complement in the big disk. In D0. So the tangle comes with I'll call it a black-white shading, but I'll do it in some other color. So the tangle comes with a black shading of its regions, so that color, the shade changes across any string.
Why don't you just call it checkerboard shading?
Yeah. Just like a chessboard or a checkerboard, right? Across any line, across those boundary lines, it must change color. So that shading changes across each string. So let me give a shading for this thing. This region I'll color this way. So this is, think of this as black white. So black, this must be white, so this is black. And this is white, so this must be black. And this region is white, so this region must be black. And this is white, so this region is black. And this region is black. Right, I think I've shaded everything. Of all of these internal disks and the strings. So none of the disks will be shaded. They are just holes. Right? We said the tangle is you take this big thing and punch all these holes. Right? There are nothing there to shade. It's just a hole. Shading. Then we have finally the last piece of data is the star regions. Please, if you have any questions, do ask. Right? This tangle is a pretty complicated object, right? I will give more examples as we go along, but right now, if you have any question, the definition I have made so far, please do ask. It's complicated, but you just look at the definition one by you get used to it after working with it a little bit. Yes.
So what I don't understand one thing.
Yeah.
What about the string starting from one mark point
Yeah.
and ending at the same mark?
No, you cannot end at this. That would sort of imply that it is not, it cuts itself. Transfer. So that is not allowed.
What about other things like you also said closed string?
Close. Yeah, here is a closed string.
Yeah, are they not intersecting?
No. So strings are of two kinds. The closed strings, which are just floating around.
They are not like intersecting.
There no intersection with anything. They just float around here in this space. And then there are these open strings which only cut at these points, and two things are not allowed to cut there. Even the same string cannot loop back on itself and cut at that point. Okay. So all of this plus now star region. So what the star region means is the following. So near. So.
Let me just put that in the definition. Open strings have two distinct mark points as endpoints.
Yeah, open strings have, right. So let me make that change in the definition. Two distinct mark points as endpoints. It's not, they cannot come from the same point. Now, around each disk, which has a positive number of mark points, one of the regions, one of the white regions, abutting its boundary is chosen and distinguished with a star. Marked near that boundary. So I'll explain this. So this star regions applies not to all disks, but generally to most of them. Most of the disks will have a positive number of mark points on the boundary. In this case, except this D4 and D5, which have 0 mark points on the boundary, all the rest have a positive number of mark points on the boundary, either 4 or 6 or something like that, right? For every disk which has a positive number of mark points on the boundary, so you look at that boundary of that disk. For example, let me take this outside disk D0. So this D0 disk has 1, 2, 3, 4, 6 mark points on its boundary. And you look at all the regions that touch that boundary. So here is a black region touching the boundary. Here is a white region touching the boundary. Here is a black touching the boundary. White, black, white. So there are black and white regions which will touch the boundary of that disk. You choose one of those regions and call it a star region for that disk. So for D0, maybe I choose this. This is a white region touching its boundary. I'll call this the star region. And I put a star near the boundary of D0 to indicate that this is the star region for D0. Then for D1, I have to select one. I can choose the same region. This white region also touches D1. I can choose this to be the star region, or I could have chosen this to be the star region, or I could have chosen this to be the star region for D1. For D4, there is no question of choosing any star region because there are no mark points on its boundary. For D3, here is a white region which touches its boundary. I'll call this one the star region for this. And for D2, let me call this the star region. So there must be a star region chosen for each one of the disks with a positive number of mark points on the boundary. It must be a white region, right? All of these I don't choose this to be the star region for any disk, right? All of these are white regions, and this is also part of the data for this tangle. Finally, I have concluded the definition of what, well, actually this is still not a tangle, this is a representative of a tangle.
Give two stars, or you want to erase one of them?
No, two. This one, this star is for the disk D0.
Yes.
This star is for the disk D1.
You will make the
Each one will have a star. Each one, otherwise it does not have the same region, because D1 star could have well been here, right? So I'll put one star for each of the disks which has a positive. Why is it?
Positive mark.
Huh?
Why is
No, I didn't follow your question. Sorry. Why? What is positive?
positive mark? We are taking positive mark like 2 and 4 like that.
No, only those things are given star points, star digits.
And positive, it's strictly positive.
Strictly positive means strictly positive. That is, if there are no marked points, that is 0, right? 0 marked points is not strictly positive, so I don't give any star region for these things or for this one. But for any others, this has 6 marked points, that is strictly positive. So then one of the regions I'll have to give. For this and this, there is no need, there is only one region there, right? The whole boundary of the disk is a single region, so there is no question of any choice. So I don't have to put any stars for this one. Okay, all of this data defines, as I said, a representative of a tangle. So what is a tangle?
No, actually, Vijay,
Yeah.
will you be using the exact location of the stars?
No. I can change it.
Yeah, can you change the star for D3 to the one on top?
This one?
Yeah,
Okay.
because I want the neighboring region for D2, the star region for D2.
For D2, D1 and D0, it's the same region which is the star region.
Earlier you had the same thing for D3. So I want
Oh,
to
yeah.
know that it can be different.
It can be different, right?
That's what she was asking.
Oh, is that what you are asking? This,
No.
huh.
Ajit was asking.
Oh, I see. No, the star region can be chosen independently for each one. For D0, I'll choose one of them. For D1, I choose one of them. They need not be the same, need not be any relationship. They can be the same, need not be the same, it doesn't matter. Okay. So now, all of this data defines a representative of a tangle. So what is a tangle? So what we are allowed to do is to wiggle this picture, right? And then we don't say that we get a different tangle. Suppose I move this slightly this way, upwards, right? Along with all the strings and the shading, all the data, I just move this slightly up or move that slightly down, or instead of this circle, I make it an oval, right? All of those things have no bearing on, it all defines the same tangle. So precisely how we say, so let phi from R2 to R2 be a diffeomorphism. Now the way I have defined it, this tangle is a subset of R2. So it's a subset with lot of other properties, right? It has some data carried along with that subset. So we can apply this phi to T, or if T is a tangle, then phi of T defines another subset of R2. And we say that it defines the same tangle if phi is orientation preserving. And 2, it defines a new tangle denoted T star if phi is orientation reversing. I'll give examples. Okay, so what I'm saying here is the following. take, you have this tangle, when are two tangles to be regarded as the same? So as I said, you can move things around, or you can wiggle it, or you can sort of stretch it, and you can make this go like this. You can do lots of things, you can do lots of wiggling, but basically the structure must be the same. I'm sure everybody has an intuitive idea of what it means for two of these pictures to be the same, right? And that is what definition actually boils down to. But there is one important thing to keep in mind, that is what kind of diffeomorphisms of R2 are you allowed. So the diffeomorphisms of R2 fall into two distinct kinds, one that preserve orientation and one that reverse orientation. For example, you could take a reflection, you could take this whole picture and reflect it in a mirror, right? Then what you get, that I do not regard as the same as this. That is an orientation reversing thing. I do not regard that as the same tangle. If I call this tangle T, I'll call that one, after reflection, I'll call it T star. But orientation preserving diffeomorphisms don't do anything to the tangle. It's the same tangle, whether I draw it this way or draw it in a slightly different way. As the connections and the basic pattern remains the same, this defines only a single tangle.
I guess you should also mention having the tangle structure on P of T obtained by
Yes.
carrying the star
Yes.
mark point.
Yes. Right.
Right.
Exactly. So if T is a subset of the plane, then phi of T of course is a subset of the plane. But what make phi of T a tangle, I have to say what the star regions are, what the shading is. I just carry over everything by phi, right? So if I move this slightly up, the same region will still, the same region I should have as the star, right? Phi takes the data also along and the subset also to a different, to the subset phi of T. So that is how phi of T is a tangle, right? Phi of T is just a subset. Phi is just a diffeomorphism of R. T is a subset. So phi of T would just be a subset of R2, but you carry all the data along, then it becomes a tangle. Diffeomorphism means, okay, diffeomorphism, well, we don't strictly need to know it. For now, diffeomorphism just means it should be one-to-one, onto, smooth. The inverse also should be a smooth map. That's what it means. But for our understanding, it suffices to just think of moving things around. That is all diffeomorphism will mean for us. You just, instead of this, drawing this D4 here, I could have drawn it here. But if I draw the D4 here, that would be different, right? I can just move it without violating things too much, without tearing or stretching. That much is sufficient for us. Okay. Right. So far we have defined what a tangle is and what the star of a tangle is, right? The star of a tangle is just the reflected picture. Okay. Now there are two simple but very important things that you can do with tangles. Okay, let this be there. We'll see lots of examples of tangles. Now this example that I have drawn is a pretty complicated example. It has lots of internal disks, lots of strings. But generally the examples that we will see while working with tangles are simpler ones. Now in order to give the definition, I'll have to take a sufficiently complicated example. But typically the examples that we deal with will have only one internal disk or maybe sometimes two, right? Typically that's all they'll have. Right? They'll be much simpler than this picture, but for purposes of definition, I've drawn a complicated one. Okay, so there are two operations that we can do on tangles. One of them is called renumbering. This is a simple operation. So remember, part of the data of a tangle is how the disks are numbered, right? If I change the numbering, if I call this one as D2 and this one as D1, that will give me a different tangle, and that is this renumbering move. But I'll have to state it a little more formally. So if T is a tangle, with B internal disks, D1, D2. So take a tangle with B internal disks. In this case, B is 5. It has 5 internal disks. And you take a permutation in the symmetric group sigma b. Now I want to define a new tangle by operating this sigma on T. So we define a new tangle. So what is the prescription? The prescription for sigma T is, as a subset of the plane, it's exactly the same as T. So as a subset of the plane with star and shading, exactly the same as T. Except in the labeling of its internal disks. So the sigma ith disk of sigma T is the ith disk of T. So here I have introduced this new notation. I hope it's self-explanatory. I said D1 up to DB are the disks of T. So instead I can call them D1 of T, D2 of T, right? Since I am dealing with two tangles T and sigma T. So Di of T is the ith disk of T, and the ith disk of T should be the sigma ith disk of sigma T. So let's take an example. So suppose sigma is 1, 2, 3, 4, 5. This permutation belonging to the symmetric group sigma phi. So what should you do? So D1 of T should be D sigma 1 of sigma T. So for sigma T, this should be D2, right? Because 1 goes to 2, right? And 2 goes to 3. So this D2. So let me anoint it with tildes. It will become D3. D3 will become D1. D4 will become D5. And D5 will become D4. So T, if T were the original one, T tilde is sigma T. The tilde ones refer to what are the disks of sigma T, right? You must be a bit careful in this prescription as to whether you are using sigma or sigma inverse in the right spot. This is the correct prescription. D sigma I of sigma T is Di of T. Okay, so this is a very simple process. I mean, writing it out takes a bit, but it's something that everybody understands. You just renumber the disks differently according to some permutation. So this is one process you can do on tangles to produce new tangles. The other is really the main thing that you can do with tangles. This is also not very complicated, but this gives rise to all the power. So the other process is something called substitution. So substitution is a way of getting new tangles from old. Renumbering is also a way of getting new tangles from old. If T was a tangle, we obtained a new tangle sigma T from T. Substitution is another process of getting new tangles from old, except in this case you begin with two of them. You begin with two tangles S and T. So suppose T is a tangle before I do substitution, let me introduce a little bit of notation. Okay, so we said that every disk of a tangle has an even number of marked points on its boundary. Now we call this number the color of that particular disk. So for example, this has 6 marked points. Now everything is even, so we may as well divide by 2. So the color of this D0 we will call as 3. The color of D0 is 3. The color of D1 is also 3. The color of D3 is 2 because there are 4 mark points. The color of D2 is also 2 because there are 4 mark points. So let me say the color of a disk of a tangle is half number of mark points on its boundary when this number is positive. Right. So as I said, D0 has color 3, D1 has color 3, D3 has color 2, D2 has color 2. But what about D4 and D5? Now D4 and D5 have no mark points on their boundary, so you can define the color as 0. That's what we would like to do. But notice that there is a difference between D4 and D5. The difference between D4 and D5 is that D4 is lying inside a white region, whereas D5 is lying inside a black region. So we want to give different colors for D4 and D5. So 0 alone will have come in 2 variations. So it is 0 plus if no marked points and white region touches the boundary, and 0 minus if no marked points and black region touches boundary. That is shaded region. Now I have said touches boundary rather than lies in a white region or black region in order to account for the fact that the external disk also could be of color 0. So if the external disk, the white region touches the boundary of the external disk which has no mark points, then we will say the external disk is of color 0 plus. If a black region touches it, then we will say the external disk is of color 0 minus. So every disk of every tangle has a color, and what are the possibilities for the color? The set of colors is denoted, let me just denote call, and what can it be? It can be 0 plus, or it can be 0 minus, or it can be 1, 2, 3, all the natural numbers. All natural numbers together with 2 varieties of 0, 0 plus and 0 minus. There are no mark points and it lies in a white region or lies in a black region respectively. Okay, so these are the colors. Now I need this definition in order to say how do you substitute one tangle in another. So how am I doing for time? Okay. So I want to define substitution now. So let T be a tangle with B internal disks of colors. Okay, so there is D1, D2, D3, D4. Each one will have a different color in general. So of colors K1, K2, K3 up to K sub B. So these are the colors of the internal disk. One is either a 0 plus, 0 minus, or some natural number, right? And let S be another tangle whose external disk has color Ki, one of these. Suppose S is another tangle, suppose the external disk of S matches the colors of one of the internal disks of T. with B. Yeah, I'm assuming that this K1 up to KB there is at least one internal disk. It's quite possible for a tangle not to have any internal disk. We will look at those class of tangles closely a little later, but for now let's just take a tangle which has some internal disk of some color and take another tangle S whose color, external disk color, matches this. Then we may produce a new tangle by substituting S into the ith disk di of t. So what does this mean? What does substituting S into a disk of t means? What it means is the following. Let me illustrate that by an example. So let us take.
If it is more than one eye, then you will choose by some method.
No, if there's more than one eye, there's more than one possibility for the answer, right? So this substituting S into the ith disk of t, the answer will depend on which eye you take.
If I exceeds, then B.
No, there's no question of I exceeding B. We are taking S to have color equal to one of the colors of the disks of T, right?
Actually, Ravi, instead notation Ki of T.
For
So you're saying that if there is an I is other K0 of S is Ki of T.
exactly, yeah, that is okay. So let me put in one more notation here. The color of the ith disk of T is denoted Ki of T. As you would expect, right? Initially I call the disks of T D1 up to DB, and then I said D1 of T means the first disk of T. Similarly, K1 up to KB are the colors. This K1 is actually K1 of T, K2 of T, so on. And so what I am saying here is that i.e. the color of the external disk of S is the color of the ith disk of T. When that happens, we can produce a new tangle we are going to call something. But how are we going to produce this tangle? I want to do that in one example. So suppose you want some element, some tangle inside this third disk of T. So the third disk of T, so example, D3 of T has color 2, right? There are 4 mark points, so its color is 2. So I can take any tangle whose color is 2, whose external disk has color 2. So let S be a tangle whose external disk has color 2. And incidentally, as a notational, such a thing is called a 2 tangle. A 2 tangle is something whose external disk has color 2, right? So take S to be any 2 tangle. For example, let me shade it also. And let me put the stars. The star region for this outside is this white region, the star region for this is this, the star region for this is this. Okay, so this is an example of a 2 tangle, right? Its external disk is of color 2. Its internal disks also are of color 2. Let's call this D1 and D2 for S. So this is S. So this is D0 of S. This is D1 of S. This is D2 of S. Right? So for K0 of S, K1 of S and K2 of S are all equal to 2. Each of these boundary circles has exactly 4 marked points. So all the colors are 2. So what am I saying over there? What I am saying is it's possible to take this S and plug it into T and produce a new tangle. So how do I plug it? Now I just want to fit this S inside here. Inside here in what way? See, there are 4 strings that are coming out, right? This one, this one, this one and this one. And on the other hand, here there are 4 strings here also. So you just match the strings, right? You match these 4 to those 4 and see what happens. But in matching these 4 to those 4, there's a further thing. See, I could have put my S like this, or I could have turned it around and put it like this. There are 2 ways of matching. And that is exactly the reason why we have this star regions present. So the matching, so substitution is to be done. Okay, so that this is not, so maybe let me say that this has one additional floating loop. Otherwise it won't matter which way I did it. Okay, substitution is to be done in such a way that the star regions match. So that is, I take this S and then turn it like this so that this star region and that star region match, and then I plug it. So
Star region for D0 of S.
yes, yeah, star regions match. The star region of D0S must match star region of Di of T, more precisely. So let me plug it in and see what happens. Essentially what it means is, let me erase whatever I have written inside here. So what I have to do is I have to draw S inside here after turning it like this. So when I turn it like this and look, I will get something like this. See, I have matched the star regions. Let me also shade. This was the shading. So now I have produced an object that looks like a tangle, except that there is something going on inside some disk, right? In tangles, nothing is supposed to go on inside any of these disks. So you just erase this part. Now you see, you have you can erase the stars as well. No stars. This external star of S and this star will just go away. Everything will go off. Now what you have produced is a new tangle, right? And this tangle.
You should have to number the disk.
Yeah. Oh yeah. Right. Yes. Yeah. We have not quite produced. We have just produced one picture. To make it a tangle, I still have to specify how the numbering is to be done. So that I'll do over here. Okay, so how is this tangle supposed to be numbered? See, what we did was we had the first disk of T, the second disk of T, and then the third disk of T. In the third disk of T, I substituted this tangle S, which had 2 of them. This was D1 and this was D2. That is the
Floating loop you missed out.
Ah yes, this floating loop will go, when I turn it over here, will go down there. The reason I did this, if I had substituted the other way, if I had rotated this like this and substituted, the floating loop would have gone somewhere on top there, right? That would have given a different picture. Okay, so how do I number the things? So initially it had D1, D2, and now instead of D3 I have introduced these two new ones, the D1 and D2 of S. So I will call this one D3, that one D4. So this one would be D3, this one would be D4, and then this 4 and 5 will become therefore 5 and 6. So this will become D5, this will become D6. So let me state all that here, how exactly the disks of are numbered. So first notation, so the substituted tangle is denoted, you begin with T and then you are composing with S, but there are many ways of composing with S. In the ith disk of T, so you put in a Di or an I there. So it is T circle DIS, that means you are plugging S into the ith disk of T. Once I say that, everything is determined, right? There is only one way of plugging S into the ith disk of T so that the stars match. No, there is no ambiguity at all, there is only one way of doing it. And the disks of this new tangle are labeled from, so how many are there? So how many disks are there, right? So initially your T had B number of disks, right? So are labeled from, so let me, this is an aside. So if T has B of T number of internal disks, and S has B of S number of internal disks, then this new one, how many will it have? Everything except one still remains, right? And everything in S is still going to be there. So it is B of S plus B of T minus 1, except the one that vanished, I erased one. So labeled from 1 to B of T plus B of S minus 1 in the following order. And that's the order that I just said. So first I minus 1 disks of T in order, all B of S disks of S in order, and remaining disks of T in order. This is the numbering of the final tangle, numbering of disks of the final tangle. So this is the other operation on tangles, which takes two tangles with some compatibility conditions and produces a new tangle out. Okay, renumbering and substitution. Okay, now let me do some examples for these with some simple tangles. Both for renumbering and for substitution, I want to do some simple examples. This will be used later. Okay, so tangles called S and T. So tangles are denoted Why don't we? It must be shaded. It must be shaded. Actually, even in S, I think I didn't shade it because I added it later. This must be shaded this way. It must be shaded. Thank you. It has to be shaded. So tangles are denoted by symbols such as we already saw S, T, but then I want to give names. So there is this tangles I, M, TR, ER, EL, R, U, etc. Okay, they just common some letter names, but I have listed those because those tangles are specifically important. This class of tangles that I will explain, we will need to understand each one of these tangles in some detail for what comes later. Okay, so now I just want to explain one tangle which is called M, right? So the tangle M is the following. Actually, it is not one tangle. I'm going to. Let me begin with some simple things, then I'll come to subscripts, superscripts. This tangle M is actually not a single tangle, it comes in a family. I'll illustrate one of these tangles. So here it is. It has two internal discs and one external disc, right? The tangle M has two internal and one external disc. Then there are these lines, which strings.
It's a question. I T R E R E L R U etc.
Yeah, there's a whole family.
I M T R E R E L R U etc.
Oh, it forms a sentence?
No, I'm joking. This is a question that is being asked.
Are you etc.?
What is EREL?
No, I am TREREL. Are you etc.? Okay. Okay, so this is an example of one of the many multiplication tangles possible. This is the so-called this M stands for multiplication. This is called the 3 multiplication tangle because there are obviously 3 strands and the shading goes like this. And the star regions, all of them share the common star region. This white region here is the star region for all those disks, D0, D1 and D2. And by the way, there are different conventions, so for now I'll use this convention, I may change it later. D1 is the bottom, D2 is the top one. Okay, so this tangle is called the multiplication tangle, and I want to illustrate something about this multiplication tangle. So what I want to illustrate about this is, I want to illustrate what is the star of this tangle, right? That is when you reflect what happens, and I want to illustrate when you renumber what happens and what's the connection between the two. So let us see what these various things are. Let me see if I have to say anything else. Okay. I think probably I can erase this. No. Okay. So I begin with the multiplication tangle M and I ask what is M star? So that's the first question I want to answer. Just by definition, right? By definition, M star is obtained from M by applying a orientation reversing diffeomorphism of 2. For example, reflection, right? You could take reflection along any line, that is an orientation reversing diffeomorphism, and apply it. So let me reflect it, say, along this line.
I guess you should observe that it doesn't matter which orientation reversing map you take.
Yeah, that's true. It doesn't matter because we said the composite of any two orientation reversing maps is an orientation preserving map, and we said that under an orientation preserving maps, two tangles which differ by that are exactly the same. So it doesn't matter which orientation reversing map you take, you will get the same tangle T star. Or maybe I won't reflect along this line, I'll reflect along the other line. Doesn't matter, but it's more convenient to. So let me reflect in a mirror of this kind. Right? In that horizontal mirror, I will reflect this angle and see what I get. So that oval still remains like this. And I still have these 3 lines. But observe how the numbering has changed. Now D1 is the top, D2 is the bottom one, and the star regions, they are just carried over. So whatever the region to this, so the shading is this. And again you observe that the star regions for all these D0, D1 and D2 are just this same one. The one on the white region on the right side. Right? So you see that the tangle M is that, the tangle M star is this. But this by definition is what we said comes from M by renumbering. Right? So note that. If sigma is the transposition one, 2, then by drawing this, what we have seen is that M star is the same as sigma M. Now we could ask, is this the same as M itself? Right? So we can ask the following question: is this tangle the same as M or is it different from M? So how do we know whether this is the same or different from that picture? It looks different, right? Here D1 is above and there D1 is below, so it looks a bit different. But how do we actually know whether it's different? That means I'm asking, is there an orientation preserving diffeomorphism of R2 which takes that picture to this picture, preserving the stars, preserving the shading and preserving the 1 and 2, right? Now it's not, I don't know how to answer it formally, right? But I'll try to explain why that's not possible. So in order to explain that, what I'll have to say is, first one can do the following. Once you have a tangle and you can begin with the star region and number the points on each boundary disk, right? Beginning with the star, you call this the first point, call this the second point, this the third point, 4, 5 and 6. You can do this for each one of these disks, right? So for this one, this is 1, 2, 3. You have to fix a sense. I'm numbering it in clockwise fashion. 1, 2, 3, 4, 5, 6. And this one, 1, 2, 3, 4, 5, 6. Okay. Now what you should notice is that when you perform an orientation preserving diffeomorphism, this numbering will be retained. Numbering will be retained means, here you see the 1 of disk D0 is connected to the 1 of disk D2. After an orientation preserving diffeomorphism, this will still be the case. Right? The numbering, remember, depends on, I have chosen a certain sense. I have chosen this clockwise. Right? So this will still hold in any tangle which is equivalent to this tangle after a orientation preserving diffeomorphism of R2. Whereas in this picture, if you do the numbering, this goes like this. Here the 1 of D0 is connected to the 1 of D1. There the 1 of D0 is connected to the 1 of D2. So after an orientation preserving diffeomorphism, if you believe what I said, this numbering is going to be retained, these two cannot become equivalent, right? So these two are indeed different tangles. M is one tangle, M star is a different tangle, but M star is the same as sigma M. Okay, so this is one thing I wanted to illustrate. Maybe I will do just one more thing. Yeah. The other thing I want to do with the multiplication tangle is to substitute it into itself and see what happens. So what is so first, does this make sense at all? Does it make sense to substitute M into itself? What would it mean? When can you substitute one tangle and another? You can substitute this tangle into this disk D1 of this tangle, provided the external color of this one matches the D1 color of this one. And all colors in this are 3, you see. The external disk is of color 3, internal disk is of color 3, this both internal disks are of color 3. So it does make sense. And what happens? What does it give? So let's begin with this. This M is this M. It has 2 disks, which D2 is the one on top, and D1 I'll draw big. And then it's connected by these strings. So in D1 I have to substitute another copy of M, right? So let me do that. So here, this is D1. Inside this I have to put in another M. M has 2. And then erase the boundary. So I get this picture, but what is the numbering? Originally this was D1, right, and this was D2 for that big M, this outside M, and this inside M has a 1 and a 2, so this will be the 1, that will be the 2, and this will become a 3. So now you get this thing which is 1, 2, 3, very similar to the original multiplication tangle, except that instead of just 2, there are 3 of them. Now as an exercise, check that this is also equal to M circle D. This is a very easy exercise. Okay, I'll stop here. We'll continue. Huh? Everything. It's correct. That's correct.